Final talk of the session will tell us how to do pen and paper style equational reasoning in an interactive theorem prover using equality saturation. The talk will be given by Markus Rossel, and there are many co-authors. I will read them out. Rudi Schneider, Thomas Kœhler, Michel, Steuwer, and Andrés Goens.
Right. Okay, thanks. I can tell it's the sleepy time of day, so I hope to get you through the next 20 minutes until the coffee break with an easy topic. It's more applied, less theoretical. I'm not going to read the title again, that's going to take a while. So I'm going to assume that everybody here knows what an interactive theorem prover is, but for those who don't, the 5-second explanation is that it's a software system in which you can state proofs and have the system check whether your proof is correct. So as an example here, I have a proof written in the language Lean, and it looks kind of like code, so it should be somewhat familiar feeling, and I hope you can all see what we're proving on this slide, right? Because I certainly can't really tell what's going on here, and that's because the actual intuitive reasoning steps that you would do on paper are just clouded in a sea of justifications, which are necessary for the interactive theorem prover to accept your proof. So if we remove those for a second, then we can kind of see what's going on, right? We're just proving a chain of equalities here, which are actually part of the proof of the binomial theorem. And this looks much closer to what we would maybe write on pen and paper. So the goal of our work is to join these worlds more closely, to allow you to write what you would write on pen and paper almost exactly the same way in an interactive theorem prover. Okay, now the way we go about this is by connecting two tools. On the one hand, there's the interactive theorem prover, as I mentioned, Lean. And on the other side, there's a tool for automated term rewriting, or more specifically, equality saturation, called Egg. And so the way we connect these two tools is by a proof tactic, which takes in a given proof goal, a user-provided set of theorems, translates these into the world of Egg, which is using an egraph and rewriting rules. Then we run the aforementioned procedure called equality saturation. And if the engine is able to prove our proof goal, then it can provide an explanation for us, which is a certain kind of proof witness, which we use to reconstruct a proof in Lean. So in a very trivial way, our approach is sound because we're producing a proof term in the end, which is checked by the interactive theorem prover. So if we produce something that is incorrect, it's just not going to pass. Now, from a more in-depth perspective, what we're doing is absolutely not sound. So in the world of Egg and egraphs, we are performing steps and running rewrite rules which aren't necessarily sound, so things can go wrong. Now, one important source of such unsoundness is the translation from theorems to rewriting rules shown at the top, because theorems come with a lot of, let's say, semantics, and rewrite rules are just syntactic transformations. So that's what I want to focus on in this talk. But before we get to that, I briefly want to explain a bit more what egraphs and equality saturation are, because maybe not everybody knows about them. So a very brief explanation of what an egraph is that it's a data structure for representing both terms, many terms, and an equivalence relation over those terms. Now, a very simple example of this would be to start with a concrete term like the one shown here, which we might use in our binomial coefficient proof. So this is just the term n plus r minus 1 plus 1 represented as an AST. Now if we want to turn this into an egraph, the first step is to combine shared subterms. So that's pretty simple. The second step is to introduce this notion of equivalence classes, which we're going to write as dotted boxes. So you can see here in this egraph, a priori, every term and subterm lives in its own equivalence class because a priori we don't know that any two terms are equivalent. But now I'm going to start shuffling things around a bit. This is still the same egraph, because in a moment we're going to perform an operation which is very common on egraphs, which is rewriting. So for that, we provide a rewrite rule, which in this case states that any term of the form x minus 1 plus 1 can be rewritten to the equivalent term just x, where the leading question mark indicates that this is a pattern variable, so it can be matched against any term in the egraph. Now, if we actually run this rewrite rule or apply it to the egraph, you can see what happens. Namely, we've merged the equivalence classes of the term n plus r and n plus r minus 1 plus 1. So you can see rewriting in an e-graph doesn't actually destroy anything, it doesn't lose information, it only adds more information to the e-graph, which is why this is a very useful data structure and procedure for using rewrite rules which would otherwise not be useful in something like a greedy simplifier. Okay, so this is an e-graph, and the final step, which is actually important, is that we are now going to only consider terms up to equivalence of children. So these boxes are now called e-nodes, so they don't represent single terms anymore, they represent families of terms. For example, the minus node now points to the equivalence class of n plus r. Okay, so that's an e-graph, and equality saturation is now simply the procedure of taking an e-graph and a given set of rewrite rules, applying the rewrite rules iteratively until we either reach a fixed point, which almost never happens, or until some user-defined timeout is reached. Okay, so equality saturation, for our purposes, is kind of a solved problem because there exists this e-graph library egg. So the part that we need to focus on in our approach is actually how to get from lean to egg and back. And that's where encoding theorems as rewrite rules comes in. Now, to first demonstrate what the differences are between theorems and rewrite rules and how we can run into difficulties, I want to show two simple examples. The first one is going to work out well. So this theorem that we could state in this way in lean just states that addition of natural numbers is commutative. And for this theorem, there's a very natural interpretation as a rewriting rule. Namely, we just consider the left and the right-hand side of the equality as the left and the right-hand side of the rewriting rule. So this rewriting rule would allow us to merge the e-classes of any terms a plus b with b plus a. Now, there is some slight loss of semantics here, because in the theorem, for example, we have a typing annotation. We say that a and b have to be natural numbers. In the rewrite rule, we lose that because it's just syntactic. But for our purposes, that's sufficient, because as mentioned, we can do some unsound stuff in the e-graph and not worry about that as our proofs are checked at the end. Now, an example of a rewrite rule that actually breaks comes from the following theorem, which is more representative of a general class of theorems, namely equations with conditions on them. So here, the theorem states that n divided by n is equal to 1 under the condition that n is non-zero. And if we, again, apply the naive translation to a rewrite rule, we get the following. Now, I hope you can see why this is a bigger problem, because this rewrite rule could easily apply in the e-graph to a term which is actually equal to 0. And the reason this is actually a problem, namely ignoring the conditions is a problem, is because recall in our approach, we actually have to do proof reconstruction at the end. So if we apply a rewrite rule which supposedly corresponds to a theorem, and then we get a proof in this way, then we will not be able to apply the theorem at the end if the rewrite rule is too unsound. So what we really need from our translation of theorems to rewrite rules is that the applicability of the theorem should to a certain degree follow from the applicability of the rewrite rule during equality saturation. Or stated more in other words, we have a requirement on which theorems we can translate to rewrite rules, namely the theorem's quantified variables should all be determined by the rewrite rule when it is applied during equality saturation. Now, from this requirement in our paper, we derive a given set of rules on which theorems we can effectively translate to rewrite rules. But I don't want to go into those as they're a bit technical. I instead want to show one example of how we go from a theorem to a rewrite rule and solve the problem of translating a theorem like the one shown here. So the one example we're going to look at is the following. It's a slight generalization of the theorem we just saw before. Namely, we generalize it from natural numbers to any field. So for any field f and any element of that field, if n is non-zero, then dividing the number by itself is equal to 1. So recall that the applicability of the rewrite rule, which should correspond to this theorem, is constrained by the fact that we want all quantified variables to be reconstructible after the fact. So I'm just going to list the quantified variables here explicitly, and I'm also going to change the statement of the theorem to match that. And now our goal is to construct a rewrite rule which somehow allows us to determine each one of these quantified variables. So let's start with the naive translation again. In that case, you can see that if we apply this rewrite rule during equality saturation, we obviously know what n is, And we also happen to know what f is because this division operator is just syntactic sugar for a more underlying application, which also involves the type. So the naive translation allows us to determine n and f. So next, we want to think about how to also obtain a proof that n is non-equal 0 and make that part of the rewrite rule. So the way we're going to go about this is to change the left-hand side, so the pattern of the rewrite rule, to include a term which can only be matched when the condition holds. So we're going to write something like this. So on the left-hand side, we now have what is called a multi-pattern, so a set of patterns which need to be matched in order for the rewrite rule to apply. And one of those terms is now fact of n is non-zero. And again, this term should only exist and be matchable if n is actually non-zero. And so to construct such a term, we use the following construction. Namely, it relies on the basic observation that any proposition holds if and only if it is equal to the proposition true, which is useful in the context of an E-graph, because in an E-graph, you can talk about equality of terms easily by them being in the same equivalence class. Okay, so P holds if and only if it lives in the same equivalence class as true, and the way we now construct a term which only exists when this is the fact is as follows. We introduce a new special E-node called fact, which lives in its own E-class, and its only purpose is to point to the E-class of true. And what this means is that the term fact P for any proposition P exists only if P is in the same E-class as true, which recall holds if and only if P is true. So fact P exists only if our condition holds. So that's why this multi-pattern construction works. The rewrite is only going to apply when fact of n is non-zero exists. And in that way, we know if this rewrite was applied, then during proof reconstruction, we can query the E-graph and ask, hey, how did you figure out that n is equal to non-zero is actually in the same E-class as true, which is going to yield us a proof of H. So we have that covered now too in this setting. Now the final quantified variable is a bit different from the others in the sense that it's a type class instance. And type class instance or type class synthesis isn't really amenable to be encoded in an E-graph. It's a much different procedure. So in this case, we want to ensure that f has a field instance by actually calling Lean's synthesis procedure. And to do that, we have to take a bit more of a, let's say, implementational view on what a rewrite rule is, which is luckily also a view that was given in the original equality saturation paper and is supported by the library. And that view on rewrite rules is the following, namely, where right now a rewrite rule consists of two patterns, we can think of it more computationally as consisting of a left-hand side, which we'll call the searcher, which is some procedure used to derive a set of substitutions for the given pattern variables. So providing a pattern is a very natural way of specifying what that procedure should be, but really it could be an arbitrary computation. Now the same goes for the right-hand side of the rewrite rule. After the searcher produces a set of substitutions, the applier can simply modify the E-graph in any way it wants based on that substitution. Now again, providing a pattern is a very natural interpretation. So what we are going to do is we're going to change the applier such that it runs type class synthesis and only proceeds if that was actually successful. So going back to our example, we're going to change the right-hand side to a bit of pseudocode here, which states that if the left-hand side of the rewrite rule matched, then run the right-hand side, which checks if in Lean field of f can be synthesized. If that proceeds, merge the E-classes of n divided by n and 1. If it doesn't proceed, simply abort the rewrite, don't apply it. And again, using this approach, we now know if this rewrite rule goes through, then during proof reconstruction, we can synthesize an instance of field f, which we can then use to instantiate the theorem above. So in that way, this variable is also covered. Okay, and since we have now covered all quantified variables, we know that when the given rewrite rule applies, during proof reconstruction, we should be able to actually apply the theorem above, as we can find an assignment for each quantified variable. I write should be applicable here, because recall, the procedure that we run in the E-graph isn't necessarily sound. We can do some unsound things. So since we can't give theoretical guarantees, the question becomes, can we give practical examples where our procedure does actually work well? And we have 4 of those in the paper. I just want to show you 2. The first one is the example we saw in the beginning of the binomial theorem. Recall that originally we had to provide many justifications for why each of these proof steps actually holds. But using our tactic, we can actually rewrite this as follows, which is using our tactic called egg, we can provide all of the equational reasoning steps without any further justification and just move all those justifications to the top, where this plus cast indicates a set of lemmas for casting between natural numbers and reals, and the plus real provides a set of lemmas for real arithmetic, and the gamma stuff are just 2 additional lemmas we need in this case. And you can see here that this is pretty much what we would have written on pen and paper. And here, precisely, we're using an approach actually called guided equality saturation, which splits up one long run of equality saturation into multiple sub-steps, which in this case simply correspond to the equational reasoning steps that we provide explicitly. So that's the first example. The second example I want to show you comes from the domain of functional array programming. So there's this paper shown here in figure 6, which introduces a bunch of rewriting rules for the purpose of optimization. And in the paper, they also prove correctness of these rewrite rules. In their case, they formalized their proofs in AGDA. And so in our use case, we also reproduced this using our tactic in Lean. And what we found is that for all of the rules that they show, first of all, these rules involve length index lists, so dependent types, as shown in the first example. And in the second example, we also have to handle binders. And in all of the examples that they formalized, we noted that we could solve them by just performing induction and case splitting up front, and on all sub-goals produced by this, running our egg tactic. And we're able to solve all of the theorems just in this way. Okay, now before I finish, I also want to mention 2 items of related work. One is called Coquetier, written by Thomas, who might be in the room or at least is at this conference. It's a very similar tool, but written for the ROC theorem prover, which also translates theorems into rewrite rules in egg, but more at a vernacular level. In our approach, we go more to the underlying type theory level of Lean. And they are also able to prove other kinds of goals like existentials. And the second very closely related item of related work is the grind tactic, which was more recently released by the Lean developers. And this tactic also is based on e-graphs, but it also integrates more SMT-based techniques like satellite solvers. And we have a brief comparison to their tactic in our paper. We were able to solve some goals which they weren't, but it is currently still unclear when our tactic proceeds and theirs doesn't, as there isn't that much existing documentation for their approach. Okay, and with that, this is a QR code to our implementation. Definitely check it out if you're interested, or check out the grind or the Coquetier tactic. And with that, I'm open for questions.
Thanks for the talk. I see many questions.
Thank you. This is very nice. About the example on slide 52, where you showed just the equational reasoning steps, here, if you wanted to skip all of the steps and go straight from the beginning to the end, would it still work?
No. So this is a case where, so this approach of guided equality saturation was derived precisely from this need of handling larger examples, because equality saturation has a tendency to just explode the e-graph. So yeah, in this case, we might be able to skip some steps, but I'm sure I tried it without any steps and that didn't proceed. It would just blow up the e-graph too much. Yeah. But I think it's a very nice coincidence that the theorem proving use case is very naturally lends itself to this guided equality saturation approach, because it closely resembles what you might do on pen and paper. You just add another equational step.
Yeah. Hi. Nice talk, thank you. So I'm curious what you call an explanation. In the beginning, I'm assuming that sometimes the proof assistant will reject correct explanations. Is that correct? The
proof assistants will correct,
so if I have a correct explanation, right, it might be the case that the proof assistant would reject that even though it's correct.
I think Well, if that is the case, that would just be a bug in our proof reconstruction. So as long...
Maybe not necessarily a bug, but is it possible for the user in that case to like somehow interact with the explanation in order to get the proof assistant to accept it?
No, so the only way you could currently interact with that in our implementation is you can look at the explanation, but that's not going to be a lot of fun. But yeah, we don't currently have an approach to massage the explanation into something that the theorem prover could accept. That's actually a good point. Yeah, we should support something to, let's say, to fix up the broken parts in an interactive way. Yep.
Thank you.
Hi. Here.
Hey.
Thanks for the talk. It was very nice. I was wondering, so the way I understand things for now is basically when you're trying to prove a precondition, you're basically proving this inside of egg by doing basically only equality reasoning. Would it be possible instead to call in the automation of Lean itself the way you do for type classes? And also one thing that or like somehow use because I feel that this is quite limited, that the only hypotheses that you can discharge are those that are provable purely by equational means. Mm-hmm. I have the feeling it will not go very far. Mm-hmm. So have you thought about this?
Yeah, so first of all, yeah, we also considered adding other decision procedures to discharge equalities. That's, for example, something that grind would do very well. Yeah. So we take a different approach. We take more of the rewrite tactic approach, which is we can surface proof obligations interactively as we can surface non-proven conditions as new proof obligations to the user after the fact, which is, for example, used in the example shown here. I just didn't show the rest of it. And this works well in some examples, but not in others. So this is, I think, also, for example, a reason why the Lean simplifier doesn't do this, at least yet, is because once you allow arbitrary conditions to be kind of postponed, things can go wrong. But in this example, it, for example, produced precisely the preconditions that we also proved by hand. Yeah, so we have a mode for this, but it's kind of a gamble whether it works well or not. Yeah.
Okay, I think it's okay. One last question.
Right. Thank you for the talk. I was impressed by your facts. This idea seems quite clever. Could you compare it? So I think you can do conditional rewrite rules where you can depend on the analysis data, the analysis data to do conditional rewrites. Mm-hmm. And this example where you have division by zero is, a standard example in which if you try and use the analysis data to decide whether you can or not apply the rule, you might just get into trouble because at some point you will look at n, the analysis data is not zero, you apply the rewrite rule, and then at a later point you'd figure out that n is in fact zero, and now it's all gone wrong. Mm-hmm. So would you mind just comparing a little bit how you can not have this issue with fact? Maybe I think I didn't get it fully, but it seems quite clever.
Yeah. So here, in order for this rewrite rule to go through, you in a sense need to proactively already have proven that n is non-zero, right? So in this case, if you haven't yet proven that n is not equal zero, the rewrite rule won't go through. So in that sense, it's kind of the other way compared to the analysis approach, right? Does that answer your question? Okay. It's either given or derived some way. So yeah, as a user, you can just input facts into the egraph at the beginning, but also we rewrite on those facts, so we can also automatically derive new facts in the egraph. Yeah. But you're touching on an important point, which is if you don't seed the egraph well with good facts, then you might just not discover something like n being non-equal to zero. Yeah.
I think it's time for coffee, so let's thank this speaker and all speakers